Hello, everyone, and welcome to my talk. My name is Hendrik, and I work as a C++ developer for the Rosen Group in Lingen. I have been interested in Rust for several years now and have also already given a couple of trainings for beginners who want to learn Rust. And this is a little bit different than that. This is an introduction to the Rust programming language for the unique perspective of C++ developers. So I assume no prior knowledge of Rust and intermediate knowledge of C++. This should be sufficient to follow along here. We will look how Rust works in general and where the differences and similarities to C++ lie, features of Rust in general, and of course, this cannot replace like a full day training of Rust or you digging into Rust books yourselves. It's just like a 90-minute appetizer if you want. Yeah, maybe you are the type of listener who wants to follow along, and this is possible. One possibility is that you now have a look here at the link, this tinyurl.com/y6exty57. This is a link which will take you directly to the slides. And if you don't want to type that into your phone or your laptop, you can also scan the QR code here in the upper right corner. This will take you to the slides as well. And as it is with ACCU, the slides will also be uploaded to the ACCU site at the end of the talk. And then you can download it there as well if you want. On the slides, there are a couple of links to code examples, which will work when you have that for yourself as well, but you can also look at me working on the code, for example. And it's all archived for you, so you can play around with the code later. So feedbacks and questions. So please ask a lot of questions using the Q&A system of Zoom. I will try to answer them all during the talk. We will come across like natural chapter marks, and there are slides which indicate that I will pause now and answer some questions now. After the talk, I will be in the Gathertown room for an extended Q&A, like you can see here in the screenshot in the upper right corner, and there you can ask me questions as well. And also feel free to approach me in the virtual venue in Gathertown and just ask me questions or give me feedback to the talk if you want to. When the conference is over and you still have questions, so here on the slides you find my social media details, so you can send me questions on Twitter or LinkedIn or give me feedback there if you are interested in doing so. Yeah, and I hope that you will enjoy the talk. And I will start the talk with just a short disclaimer. So I will do a talk about a programming language. And I don't like language wars, and I think neither should you. So programming languages are not in general better than others. They are just different. And Rust and C++ are clearly different, and this is okay. And maybe we can learn from each other, and we can take ideas from C++ and apply them in Rust and vice versa. And of course, this cannot be a complete Rust tutorial. This would be like a several-day workshop, and I will only highlight here interesting features compared to C++. And I will also have slides which will point you to free and also paid resources if you are interested in learning Rust afterwards. There's also the possibility for you to try out coding in Rust. There are several ways we can go here. So since this is largely a C++ conference, I think most of you will know Compiler Explorer, and Compiler Explorer also supports Rust, which includes executing a compiled Rust executable. There's also something called the Rust Playground, which is, I think, or we can say it's something similar than Compiler Explorer. It can also compile and execute your code, and it has some more Rust-specific features like executing Rust unit tests, looking at LLVM intermediate representation, and a little bit more. And if you want to try out on your machine, I've also here the link if you want to install Rust, which is pretty easy if you're running Windows, Linux, and Mac. And Visual Studio Code is supported by Rust as an IDE, which has a great plugin called Rust Analyzer, which you can use for static analysis, compiling, and running your code. And we will see that also later. So what is my motivation for giving a talk about a programming language? So I saw this here on Twitter, where people tweet what kind of programming languages they have learned in the past. And I think this tells us a lot about the sheer amount of different programming languages out there. There's a lot of them, and I think maybe possibly more than one person can learn in a lifetime, unless somebody proves me wrong here. And they all have different paradigms, styles, syntax, peculiarities, areas of use, areas of expertise, and so on. And learning a new programming language, or at least having an informed look at it, can open up new ways of thinking about problems, algorithms, and code in general. And therefore, I personally love learning new programming languages, and I will probably never stop doing so in my life. And this is my intention here for the talk. So my intention is not to convince you to only use Rust and abandon everything else you have used before. Or maybe my intention is also not to convince you to stop using programming language X you love so much. I just want to motivate you to have an open-minded look at Rust and see for yourself if this is a language which interests you, or maybe the paradigms of Rust are interesting for you and you can apply these things to problems you have in your hobby projects or at work. One motivation for talking about Rust in general is, for me, is tooling. So in my opinion, programming languages should include a lot of tooling to make life easier for the developer. So if I want to set up a new project, that should be easy. There should be a build system, a package manager, a testing framework, and a static analyzer. These are all the things I love using, and there should be batteries included into the programming languages. This is something C++ does not have in a batteries included fashion. There are a lot of de facto standard tools in C++ like CMake, Google Test, VC Package, Conan, Clang Tidy, CPP Check. And this is all great. But one thing I love about Rust very much is that all these things come with Rust itself. Rust has a tool called Cargo, which is many things in one executable. It's a package manager, it's the interface to the compiler, to the test runner, and many more things. And this is really cool. And the other thing I love about Rust tooling is that there is like a standard repository for open source packages. The website crates.io features a lot of packages you can just build into your projects using Cargo. And here the name crates is a pseudonym for packages in Rust. And this is also really cool. You can have, of course, a lot of private repositories in your company, but having a huge open source standard package repository is really cool. Yeah, and this is something I really enjoy about Rust. The other motivation for talking about Rust is safety. So having a memory safe program is something which is like a standard philosophy of Rust. And here we have an example of C++ code, which has a very obvious mistake in it. So we have a standard vector with some ints in it. We get a reference to the first element of this vector. Then we are doing a pushback. So we are extending the vector by the element of 12. And then we print our reference. And from a naive point of view, people would be expecting, it should print -7. This is the first element of the vector. And here we have the reference. But here what the compiler will print is 0. And why? Because we have invalidated the reference by pushing something to the vector. And this is something which C++ compilers do not catch. So even if you crank up the warning levels to W all, W extra, this will not be caught. Maybe static analyzers can see that, but the compiler itself cannot see that, or maybe it can see it, but it will not warn us or halt the compilation. And of course, this error here in 4 lines of code on the slide is pretty obvious, but these kinds of errors, they occur in production code as well, and usually they are not that obvious in production code. And this is something which Rust tries to prevent us from doing. So here is the error message you would get if we try to have the same code in Rust. So here we get a compiler error which says cannot borrow v as mutable because it's borrowed as immutable. No? It tells us, okay, here we're trying to get a reference to the first element, here we're doing a push, and here we're doing something forbidden with that. Now, and this means if we translate it to C++ speak, it's like we have a constant reference, which we're not allowed to have because we modify the underlying vector. And Rust tries to prevent as much as possible of these errors at compile time using a system called ownership and borrowing, which we will discuss in detail later, and which enables the compiler to reason about who has a reference to what, and is that a good thing or not a good thing. If it's not a good thing, then the compiler will halt compiling the program. And one thing to say here, the error messages are really great. Yeah, if you have a look at that, we get the line numbers, we get here some markers where something bad is happening, we get red squiggly marks under a line where something really bad happens. So the design of the error messages is really cool. So let's still talk about motivation. Another thing about Rust is learning curve. Yeah? Here, this is a keynote from Rust conference, and where the statement is, Rust is a language empowering everyone to build reliable and efficient software. And this says it all, in my opinion. Rust aims to be a well-designed language in terms of syntax, features, tooling, documentation, in a way that the learning curve is not steep and that you can read a couple of tutorials or watch me talk for 90 minutes and then start exploring the language without being frustrated. And although Rust is often labeled as a systems programming language, and you can do almost everything with it. So it's a systems programming language that you can write modules for the Linux kernel with it, but you can also do basically everything. You can write command line utilities which help you in your day-to-day work. You can write UIs, web apps, databases. You can write algorithms, whatever you want. So there's a wide variety of areas to explore with Rust. And so what is Rust? So this is taken from the Rust homepage. And here we can discuss a couple of facts about Rust before we have a look at source code. So the first thing is here, Rust has no runtime or garbage collector. So it is a programming language which compiles down to assembly. It has a self-hosted compiler with an LLVM backend, and it tries to have comparable performance to C++. Rust focuses on memory safety and eliminating many classes of bugs at compile time. This is what we've been talking about with this ownership and borrowing system, and this example with the invalidated reference. Rust tries to have useful error messages. We have seen one, for example, and it has a package manager and build tool which are integrated. This is what I talked about, which is really important to me, and setting up a new project with dependencies and building and testing it is super easy as well. So, and this is basically what Rust is. And now we get into resources for learning Rust and then into source code. So let's start with some references here. So I've seen in the schedule for Rust that here at ACCU 2022, there are 2 other talks which will also talk about Rust. One is on Friday. It's coroutines, C++ versus Rust from 11 to 12:30. And this sounds also very interesting. And maybe if you are a beginner to Rust or you have listened to my talk today, maybe this is like the good next step, going to that talk and learn about coroutines in C++. And then I would say maybe it's asynchronous programming in Rust. That sounds cool. And then there is a second talk, Neutron, writing a single tasking DOS for ARM microcontrollers in Rust on Friday as well from 2 to 3:30. This sounds interesting for the embedded crowd. So check out these talks if it's something for you after talking to me today. And I will also give now here a couple of free resources to learn Rust. And there are a lot of them out there. The first thing is the Rust book, which is an official resource and covers a lot of topics and is a great tutorial. So this is like the official free Rust learning book. The Rust cookbook and Rust by example are more driven by actual tasks or problems you want to solve. So they have a list of things you might want to do. So for example, you might want to do something with, I don't know, a two-dimensional matrix-like data, or you want to write to a file or serialize to JSON. And then in the Rust cookbook and Rust by example, you find basically recipes how to do that. Then there's a teaching material from Ferris Systems, and Ferris Systems is a company which you can go to and get paid Rust training. So they come to you, I don't know, on site or virtually and give Rust training, but they have also like a free version of slides you can go through to learn Rust, which is also really cool. And the last thing here is Explain RS. This is not really a tutorial, but if you're starting learning Rust and maybe you are confused by what syntax is doing, you can go to that web page, paste your code in there, and it will try to explain in English what is going on there in your code and explain the syntax. This can also be really cool for beginners. So next thing is paid resources to learn Rust. So I'm a huge fan of programming languages books, and I actually collect programming languages books. So maybe if you are the book learner now, you can listen to me. If you're not a book learner, then go back to the free resources or hire a trainer. But these are actually my 3 favorite Rust books you can buy. There is Rust for Rustaceans, which is more like an advanced level book. So if you already know Rust on an intermediate level, then you can have a look at that. And Rust in Action and Programming Rust, they target more beginner and intermediate Rust users. So if you've worked on a couple of tutorials or written your first few applications or worked through a couple of trainings, then you can have a look at these books. And I would, if you would ask me, I would recommend buying these. They are really, really good. And with that, I think we can go now to the actual stuff, which most of people would be interested in, like syntax and features of the language. And I will start with a little bit of the comparison of the syntax. Here on the left side, we have Rust code, and on the right side, we have C++ code, and they are both doing exactly the same thing. So they have an add function. We define 2 integers, we add them up, we take the result, add 5 to it, and then print it out. So most people are hopefully familiar with the C++ code for it. And now we can walk through the differences we see here in the Rust code. So here in C++, we have 2 const variables with autos or type deduction, a type inference to int. And here on the left side, in Rust, we have let. Let is a statement to introduce variables in Rust. And the first major difference here is we don't specify const. And this is because variables are immutable by default in Rust. That immutable is basically const, or what we call const in C++. So we cannot change this variable a any longer in C++, and we cannot change it any longer in Rust as well. Just in C++, we have to write const. In Rust, we don't have to do it. It's implicitly immutable. If we want to have a variable which we can change later on, we have to specify it here with the mut keyword, which stands for mutable. And this allows us to do this here, taking the variable and adding something to it. Now we have a look at the add function itself. So the syntax is a little bit different. So fn introduces a function in Rust, then the function name, then the parameter list, and we have a parameter name followed by a colon and then the type. So i32 is a 32-bit integer, assigned integer in Rust. And after that, we have the arrow with the return value. And then in curly braces, we have the actual code of the function. And here we see some interesting things. So here in our main function, we have the semicolons terminating the line as well in C++ as in Rust. But here we don't have it. And it looks maybe like a typo, but I didn't make a typo. So no semicolon has an actual meaning in Rust, and it means that the value here is returned. So the function here will calculate x plus y, and then here's an implicit return statement because we have no semicolon. We could write a semicolon here and write return x plus y, but we don't have to because we can do it shorter in this way. And yeah, the last difference I want to point out is that here we don't have something like cout and the stream. We have a print function, and it's here println for print line, and then we have this semicolon. And this semicolon is not part of the function name here in Rust. The exclamation mark. The exclamation mark in Rust means that this is a macro. So print line here is a macro, which we will talk maybe later about in the end if we still have time, or you can ask questions about it. But the difference here is that we have macros, and we know when we are calling a macro because we have this exclamation mark here, which is like needed if you want to define a macro. So I talked about that things are immutable in Rust by default, but the interesting thing is there's also a const keyword in Rust, which means something different than const means in C++. So here again, I have two code snippets comparing C++ on the right side and Rust on the left side. And what we have here on the right-hand side in C++ is a const expr function, which calls a Fibonacci number. Yeah, and we call it for the number 5 and the number 8. And we print it out with std_cout. This is something most people in C++ will be familiar with. And here on the left-hand side, we have how that would look like in Rust. And in Rust, const expr is const. So a const function roughly translates to what a const expr function is in C++, so something which is calculated at compile time. We can use it for compile time functions or compile time constants. And the difference here to C++ is, for example, here we declare a compile time constant, so const s, which is the 8th Fibonacci number. And in C++, we can use auto. But in Rust, if we have a compile time constant, we have to give it a type. So there's no type inference here. So we have to say it's a 32-bit integer if we want to make it a compile time constant. And these compile time constants in Rust are inlined wherever they are used. So it's basically identical to simply replacing the name with a value. And again, notice here in Rust the missing semicolon and return statements. We can just here return 1 or return fib n-1 plus fib n-2 here without having to write return and a semicolon here. Yeah, and now I want to talk about variables and references. So how does Rust reason about values and references to make sure that there are no problems? So each value in Rust has a variable that's called its owner. So if I write let a equals 25, the value 25 is owned by a, and it's a 32-bit integer. And there can, of course, only be one owner at a time. And when the owner goes out of scope, the value will be dropped and is no longer there. These are pretty much the same scoping rules that we already know and are familiar with from C++. And now here comes one of the main or major differences. So at any given time, you can have either one mutable reference or any number of immutable references, but not both. So if I have my variable, and this means I can have like 10 or 100 immutable references to that value and variable and use them as I like, pass them around, print the value out, do whatever. This is fine, but I can only have one mutable reference, or a reference I use to change the value. And if I have that, I'm only allowed to have this one mutable reference. I cannot have two or more, only one. And I also cannot have any other immutable references at the same time in scope. And these things are enforced by the compiler. And the compilation will stop if you violate these rules, and the compiler will tell you what you are doing wrong. And references must always be valid. So I cannot return a dangling reference from a function. This will be caught by the compiler and your compilation will be stopped. So now let's have a look at some examples for that. Here I have code which creates a mutable string called hello, and strings work in Rust as they do in C++. So the value which is stored in the string is stored on the heap. This is basically the same. And what we are doing here now is we are creating two immutable references, R1, R2. Yeah? They can only read the value and not modify that. And until here, we have no problem. We have two immutable references. We are allowed to have that. That's totally okay. But now here on this next line, we create a mutable reference to our string. And this is a problem. Now we have two immutable reference and an mutable reference at the same time. This is not allowed. And if we now try to use that here and print that all out, the compiler will stop and tell us that this is not allowed. We're not allowed to do that. So, but we can change the code a little bit and still make it work, which might look a little bit surprising. And this is a fairly new feature of Rust. So here I have reordered the code a little bit. So again, we have the string hello. We have our two immutable references, R1 and R2. And now I print R1 and R2, and it will print hello and hello. And now after that, in the same scope, so you see, curly braces or functions or whatever, I create a mutable reference and print it out, and it will print hello again. So, but here this is no problem. And why is that? I still have two immutable references and one mutable. And this is the case because the scope of the reference starts where it is introduced and continues through the last time that the reference is used. So R1 starts here, R2 starts here, and here is the last time they are used. And the code will compile because the last usage of the immutable references occurs before the mutable reference is introduced. The scope of R1 and R2 end after the print line where they are last used, which is before the mutable reference R3 is created. These scopes don't overlap, so the compiler allows us to have this code. And this might look a little bit frustrating if you've never worked with Rust, because we've just reordered the code a little bit to have it compile. But you might say, these borrowing errors might be too much. But remember, the Rust compiler is trying to help you prevent bugs early, preventing bugs at compile time rather than at runtime. And it will be showing you exactly where the problem is. So you don't have to track down at runtime why your data isn't what you thought it was, which can easily happen at large applications with memory safety problems and bugs. And the last thing here is I said a couple of slides ago that references in Rust must be valid all the time. And here we have a typical example for creating a dangling reference. We have a function which is called dangle here because it tells us what it is doing. It returns the reference to a string. Here it creates a string s. Hello, this is stored on the heap, all fine and nice. We create a reference to s, no semicolon here, so this is what we return from our function. And if you've seen similar things in C++, you already know that this is a problem. The value s lives until here, the curly brace, last curly brace of the function. Then s is dropped and the value on the heap is deleted. But we still here have a reference to something which already has been deleted. So we have a reference to garbage code. And this is a problem. We have a dangling reference, points to garbage data. Maybe this is not good. So and in Rust, this will not compile. And I've pasted here the error message to the slide. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. So here, the error message from Rust tells us exactly what the problem is. And if I would have pasted the whole error message, it would also point us to the line where the problem is. So this is a problem we can easily fix here. But sometimes we have to help the compiler also in figuring this out. And I will, before we go to the first end of the first chapter, we will talk a little bit about lifetimes and helping the compiler. So lifetimes in Rust describe the duration a value remains in memory compared to other values. And they are descriptive types which the compiler usually can infer itself. So usually the compiler looks at your code and says, okay, we have here two things. They live the same exact amount of time. Everything is fine. And they are used by the compiler to reason about the memory safety of our code. And since Rust usually handles this under the hood for us, we come into contact with lifetimes usually only when there are problems. And when is this? So the compiler might need our help if we store a reference to something in a struct or return a reference from a function where the input to the function are also several references. And there's a dedicated type for lifetimes, which is started by a ticks and then a name. And we can make functions and structs accept generic lifetime parameters to reason about these things. And now we will have a look at that. So I will click at the link here and hopefully everybody here will be able to see the code. Please someone notice me if this is not visible. And here's a function or a problem with the function I mentioned before. We have a function get bigger value. It accepts two references to 32-bit integers, x and y, and it returns a 32-bit integer reference. And if x is bigger than y, x is returned, and else y is returned. And this looks pretty much okay. Yeah, we have a value a, which is 12. We have a value b, which is 33. And now we're trying to get the bigger value, and we make references to a and b and give them to the get bigger value function. So yeah, if we look at that without prior Rust knowledge, we would say, why shouldn't this compile? Yeah, it might work. And we now hit compile. We wait a little bit. And we get here an error message, which I want to have a closer look at with you. So here, we get the error message missing lifetime specifier. And it underscores here our two references. It says an expected named lifetime parameter. Help. This function's return type contains a borrowed value, but the signature does not say whether it is borrowed from X or Y. Help. Consider introducing a named lifetime parameter. So, and what's the problem here? The Rust compiler also tells us what we should put in there to make it work. You see here in the angle braces, you see a tick A. This is a generic lifetime parameter, and we should put that here to all our input and outputs of the function. And what this does, it tells the compiler, hey, the lifetime of these values X and Y and the lifetime of the output reference, so the return type of get bigger value, is all the same. So we guarantee the compiler, hey, whatever we are doing here, X and Y will live the exact same amount of time as each other and as a return type. We can try that here. And do what the helpful compiler is telling us to do. And run it again and see what happens then. So now it compiles and it puts out 33. We have guaranteed now to the compiler that X, Y, and the return type live the exact same amount of time, and this is correct. Here, A and B are in the same scope. They will live the exact same amount of time, and here the return value, which is a temporary, is also in the same scope. So there are no problems with this code anymore, and we help the compiler to reason about the memory safety of our code. And sometimes, I have here another example, we can use that as well, but it won't work. So here's an example of the same code. So also please ping me if the code is not readable. So here I have the same function for an compiler explorer now fixed with these lifetime parameters. And what happens here now, I've changed the code a little bit. I've introduced A here with a value of 55. I've introduced a variable result here with no value in it. And I have here a value B, which is 33. And now I want to get result using the get bigger value function. I want to print it out here. And now what happens is we get a compiler error. And what is our compiler error? It says B does not live long enough. So we are borrowing B here, and we're printing result. And it says B dropped here while still borrowed, borrow later used here. And this looks kind of strange to a human because the return value here of get bigger value, it will return a reference to A because A is bigger. So we're printing a reference to A here, and this has nothing to do with B anymore. And from a perspective of a human, this is correct. But please remember what we've guaranteed to the compiler beforehand. Using this lifetime annotation here, we've guaranteed to the compiler that X and Y and our return value all have the exact same lifetime. And this is not true here anymore. A and result are in the outer scope, and B is here in an inner scope. So B only lives until the end of this curly brace and then is dropped. And the compiler notices that. It says, so you violated a contract you have given to me, so I won't compile the program. Although the program, from a technical perspective, could work here, since we're returning a reference to A. And this can be, so this is one of the points where these errors and guarantees can be a little bit frustrating because you're not making a mistake here. But if we would change our code and change the value of B to 335, then we would return a reference to B. B gets dropped here and we would get garbage here. So the compiler tries to prevent us from making mistakes here, although in the first place, we weren't making a mistake, really just violating a contract we have with the compiler. Yeah. And this is the end of the first chapter. And now I will have a look in the Q&A if there are already questions. So maybe I will also wait a couple of seconds if you want to enter your questions now and have a little bit of water. So I see no questions in the Q&A at the moment. Then I will continue. There will be a next. Oh, there's one. I will answer that now. Oh, now the questions are popping in. Sorry, I didn't wait long enough. I didn't see that. So the first question is, could result exist in the inner scope? It would not have the same lifetime as the other parameters. So I think it cannot, because they need to all have the exact same lifetime. We say to the compiler that everything has the same. But again, we are free to try that out here. So we can make this go away, go into here. We cannot print there anymore because this result does not exist. Yeah, okay, this works because, yeah, now this has the exact same lifetime. This lives longer. Yeah, this still works out. A question. All these compile time checks are great. Curious what compile time performance is like. I don't have a benchmark at hand here right now, but compile times are, I would say, similar to C++. So compiler is based on LLVM, and there are things which make compiling slow, which also C++ has. For example, there are generics, and generics in Rust work the exact way as templates work in C++. So this is usually something which slows down compilation. And I would say it feels similar in compile times. Maybe Rust is a little bit slower in compiling, but I have to do some research for benchmarks there. I think it's really hard to benchmark these kind of things, but it could be possible. And you asked explicitly for compile times, but I will tell you something about runtimes. So runtime, if you have a look at that, is similar to the things in C++, because all this optimization stuff is borrowed from LLVM, and Rust is not in general slower than C++ in runtime. I know you asked about compile time, but I thought it was a good point to bring it up here as well. Yeah. Any other questions I see? Wait again 5 seconds or so. It would be great if you type in your questions during the talk, then I don't have to wait here for more than a couple of seconds, but I know sometimes the questions just come to you at any time. There's a question in Discord. I cannot open the Discord right now that easily here with my setup. Maybe I will address that later, or the person in Discord can put it here for the next round of questions. That would be great. Or I will answer the person after the talk in Discord. This is also possible. And now I will continue. So the next chapter could be basically called Copy and Move Semantics. And I want to talk a little bit about how Rust and C++ differ here in their behavior. So here we have code. We have a value 5, which is stored in A, and then we have a statement here, let B equals A. And we print out A here. And this behaves like in C++. the value which is stored in A here is copied and stored in B. So copy semantics, no surprises for the seasoned C++ developer here. But we can get a surprise if we change our code just a little bit. And maybe we don't want plain integers. Maybe we want to wrap our integers in a struct because there are maybe other values in it or methods. So here for simplicity, we just have a wrapped integer, a wrapped number that stores a value which is a 32-bit integer. And we build it up here. We constructed wrapped number, and in Rust, you usually, if you construct structs without any special functions, you write the curly braces and the name of the field, a colon, and the value. So here we create a wrapped number struct with a number 5 stored in it. And then we have the statement let b equals a, and then we want to print the value which is stored in A. And to the most astonishment, if you're coming from C++, this code does not compile. From a C++ perspective, we would maybe expect that it compiles, but it does not, because here we happen to come across move semantics. And types which are not in C++ speak, plain old data types like ints or floats, have move semantics by default and have no copy semantics. So what happens here is we construct A, and instead of copying A, the value from A to B, we move the contents of A into B, and moves in Rust are destructive. So in C++, moves are not destructive, and the moved from variable is left in a value, in a, say, okay state with unspecified contents, but in Rust, the moves are destructive. So after we've moved from A can no longer be used, and this here will be a hard compiler error. It's possible to introduce copy semantics to other types as well, for example, to this struct using attributes, and we will see later how this works, but this is only possible when all contents of such a struct support copy semantics. So we could introduce copy semantics here to our wrapped number struct, but if our wrapped number struct would contain something else which cannot be copied, then we cannot make our struct copyable. So, and here, again, we can have a look at the great error message Rust throws at us. If we try to execute this code here, it tells us, let A, this is the let, and then we have here let B equals A, and we have move occurs because A has type wrapped number, which does not implement the copy trait, value moved here, and value is borrowed here after move. So again, the error message is really, really great and tells us what problems we have run into here. And again, move is a default operation for all types which are not primitive plain old data types, or implement the copy trait. We've tried to access something which has been moved from, and the compiler does not allow that. And as I said on the last slide, and this is a very important statement, moves are destructive in Rust. You cannot use a variable whose contents have been moved. And this is completely different from C++ moves, where the move from variable is left in an intact but unspecified state. And last slide before we end. This chapter is expressions in Rust. So we have seen a couple of slides before on the syntax slide that if we want to return something from a function, we don't need these semicolons. And Rust has more expressions than just the return statement from a function. We can return values from different things as well, which might look a little bit strange to the eyes of a C++ developer. For example, we can return values from an if statement. So I can write something like let number equals if x is smaller than 11.5, else 6. And everything here from the if to the end of the line is an expression. And if x is smaller than 11, 5 will be returned and assigned to the variable number, and otherwise 6 will be returned from this if expression here and assigned to the variable number. And this is true not only for example, for if, we can also construct loops as an expression. So here in Rust, we have the loop keyword, which is just an infinite loop. So a block of code is executed over and over again forever until you explicitly step out of it using a break statement. And we can return a value from this loop statement here. So we have here result, and result is equal to, and we have a loop statement. The loop increases a counter by number, and if counter is bigger than 3 times x, we break out of the loop statement, and the thing here after the break statement is the value we return from the loop expression, and this is then what will be assigned to the variable result. And this is really cool because we have with that immutable variables which are assigned values from complex calculations without having to define functions for that. So result and number are immutable variables. I cannot change them anymore. But the initial values I have assigned to them comes from complex expressions here. And of course, this is similar, or not similar, this is possible in C++ too. Yeah, in C++, I can have something like immediately invoke lambda functions and do the same. But in Rust, I don't need lambdas or closures for that. I can just write expressions and return value from expressions. And this is, in my opinion, really, really cool and useful also in practice, in real world code. And now, again, is a good point for questions. Okay. We have the first question is A not immutable? I don't know what slide this is referring to. Maybe this slide here. So here A is immutable by default. It's immutable, but you can still move a value from it and destroy the variable that way. In Rust, immutable means you cannot assign something new to it. I cannot go here in between these lines and write A is equal rep number value 27. I cannot do that. But I still can move from an immutable value. This is still possible. For slides 25 and 26, does the move occur because it is the last place the variable is used? Yeah, I have to read it again, sorry. For slide 25 and 26, does the move occur because it is the last place that the variable is used? Also, would the same error occur if the struct was copyable but not movable? So in Rust, you still... So here the error occurs because I use A again. So if I would get rid of this line here and never use A again, then we wouldn't have a problem here. This error occurs only because I use A again. And I hope this is what your question means. If the struct would be copyable, we can use here A and B as much as we want, and then it wouldn't be moved at all. It would just be copied. We have a question which is just from Discord : I think there's something missing. Maybe you can ask your question again, because from Discord : sounds to me like you wanted to copy in something else again from that, but didn't. This is again from copy the question from Discord. There's a second question. A lot of those differences look like they are compiler quality warnings, checks, and messages that could technically be implemented in the C++ model. Am I missing something? If not, why do you think there's little effort towards this? So I think a lot of these things can be done in C++ as well. And yeah, if a Rust compiler can do these things, then I think we can teach C++ compilers a lot of these tricks as well, or maybe teach it also to static analyzers like clang tidy or CPP check. I don't know. Personally, I don't know many people who work on compilers or static analyzers. Maybe there are efforts in that direction I just don't know of, but at least from my perspective, as someone who has never worked on a compiler himself, I would say it should be possible to introduce these checks into C++ as well. And I think C++ would be a little bit a better language if we have all these checks as well to help us in not doing these mistakes, which are, of course, a lot more complicated in production code than in my slideware. Thank you for the question. Yeah, and now I want to talk about structs. So we have seen structs before in the example about move semantics. And in C++, there are structs and classes, and they just differ by the default visibility of their members. And in Rust, there are only structs. And the attributes and methods of structs are public by default, at least if you are in the current module. And I don't have time today to talk about the module system. You can check this in a proper Rust tutorial, but there are also private and public things in Rust, but this is largely handled by module borders. And if you want to have something visible outside of the current module you are in, you can make it public with the pub statement, but I will not talk about in detail about that here. And again, we define a struct, we name the field, give it a type. For example, here length is a 32-bit floating point. And we construct it by giving the name of the struct, curly braces, the name of the attribute or field, and then a colon and the value we want to assign. And in Rust, there are no things like default constructors or destructors or default methods. If we want to have something like a constructor, we have to write it ourselves, and we can and will on the next slide. But since everything is public in the same module, we can just here define it this way and access the value using the dot notation. If we want to assign methods here to the square struct, we're using an impl block, and we write impl, then the name of the struct for which we want to define methods. A method is a function, so we need the fn keyword, a function name, and then much like in Python, we need to define how we want to access our struct. So self is the keyword referring to the struct itself, so like this pointer in C++, and we have several possibilities here to access our struct. We can give it an immutable reference to self. This means we are working read-only with our struct. Yeah, we're using values from the struct, but we are not changing it. So here, for example, in the area function, we are multiplying lengths with itself and returning that, and this is not changing anything about our struct. So we're doing read-only operations here, and therefore we can use an immutable reference to self. And this is a little bit like a const member function in C++. We can also use a mutable reference to self, and then we have the possibility to change the underlying fields in our struct, so we can make length here longer by the factor. And in Rust, the reference to self must be the first parameter here in the member function, and we can have arbitrarily many after that, like the factor here. There are also methods without a self argument, which are called via the name of the struct, 2 colons, and then the name. And you can build something like constructors with them. For example, here we have a new function which takes, this has the wrong type. It should be floating point 32, but typos happen. So it takes value L here and returns self in uppercase. So this is self in uppercase refers to the type of the struct, which this impl block is assigned to implement methods for. So this will be translated by the compiler into an instance of square. We can use it here as well as a type name and construct our struct here. And in our code, we can call square : u3, and then we have build a square. And this is the canonical way in Rust to do construction of complexer types. We create new functions, and new functions are taking over the role we know from C++ as constructors. And a couple of slides ago, we have seen strings. The string struct has also a from method, and from is also a canonical name for a function which creates a new instance. And this is usually when we create a struct from another struct, then we give this the function name from. This is not enforced by the compiler. It's just like, I don't know, decided upon that we use these names for that. You can give it completely different names, but people then might be arguing with you in a Rust code review if you want to push that somewhere. So we also have a vector in Rust. We've talked about it a little bit with the memory safety example. And a vector in Rust is also roughly equivalent to std vector in C++. It stores the values on the heap. You have something like push to push values in it. So and here's something interesting. So we create a mutable vector with a new keyword, and it's empty. And then I push the value 8 in it. And here you might be getting skeptic. Why does that code compile? We haven't wrote any type here or type hints here, and the compiler at this line does not know what kind of vector this is. This is a vector of ins, floats, whatever. And this is something cool. So type inference in Rust works over multiple statements. So here, Rust does not know what kind of vector it is. But here we push an 8 into it, and the compiler knows, oh, if my vec is something where I can push in an 8, then I know it's a vector of 32-bit integers. So type inference is finally decided here and works over multiple lines, which is really, really cool feature. There are also other ways to initialize a vector. There's a vec macro, so vec exclamation mark and exclamation mark, as I've told you, says this is a macro. And then I'll just write in the values I want to have in the vector. And now I have a vector containing the values 1, 2, 3. I can iterate over vectors with a for loop, like a range-based for loop in C++, where I have a for I in, and then I define how I want to iterate over it. For example, here with the mutable reference, because I'm changing the values. I can also get rid of the mut, and then I just have an immutable reference. If I want to, for example, just print out the values of the vector. And there are iterator-based functions. And here's a little bit of, let's see, not brain teaser, but something which sometimes gives me problems in the wording, because iterators in Rust are, at least from my understanding, more similar to ranges in C++. So I translate them roughly to what ranges do in C++ and not to what iterators do in C++. But this is, I'm up for discussion if someone wants to prove me wrong here. I can take my, my vector. I can call the function iter, which gives me an iterator over my vector. And then I can call the sum function to calculate the sum of my vector, store it in the variable sum and print it out. And there are a lot of functions which I can use after I get an iterator. Yeah, there's filter, map, all the standard things you can think about, which are also in the standard C++ headers for working with collections, exist also in Rust, but we use them here like in a little bit other way, because we're getting an iterator to our collection and then calling these functions. Next interesting thing are slices. Slices in Rust are similar to views we have in C++, at least to string view and studspan. And they are possibly mutable views to data which is owned somewhere else. Yeah. So if we have a look at code here. Make this a little bit bigger here as well. So here we see a little bit different syntax in the function parameters. So here, for example, I have function square, which takes an argument data, and data is a mutable reference to square brackets of I32. And these square brackets of I32 is a slice to is an array slice. And we can take this data now, iterate it over it in a for loop, dereference it, and multiply it by 2. And this is, if you want to translate it to C++ speak, would be a std span. So we have a type which indicates that we have a view to data which is owned somewhere else and we want to do something with it. C++ would be a span, and then Rust it would be this slice here to an array. And we can put an array into that, we can put a vector into that, or maybe some custom collection you have programmed which supports slicing. And if we go down to this function here, these slices, this is an immutable slice, also support all these cool iterator functions. So I can get an iterator over my slice, apply a filter function to it, and then calculate the sum and return the doubled sum from my function. And I have the same kind of thing for strings. So something which is similar to a string view. And this is a string slice, which is written as %str. And this is a view to textual data, so possibly a string somewhere, and I can do things with it. And it works pretty similar to the other slice here. And if we look down here in the code, I have vectors, I have an array, and I can put that into the print array and into the square function, and it works because these types support slicing, or as we would say in C++, a span. And this is also really cool. I have to look a little bit at the time. I have still 25 slides and only 20 minutes. Let's see how far we get. So next thing I want to talk about is traits. So traits have no really equivalent in C++. It's more like interfaces, which you might know from languages like Java and C#. And a trait specifies functions which a struct needs to implement if it wants to fulfill this trait. So we have here this trait, we have the trait keyword, we give the trait a name, and we define that trait shape means you have a function area, which has an immutable reference to self and returns a floating point 32. And if I want to implement that for a struct, I have a special impl block. I write impl trait name for struct name, and then I implement the function which is specified in the trait. This is all fine, I guess, looks like interfaces. And then I can write functions which accept a trait. So I can have here this print area function, which has a parameter shape, and it is an immutable reference to something which implements shape. This is how you can read it here. And then I can call the area function here. So it's not a reference to a square, it's a reference to something which implements a shape. And this is a generic function. So this is a little bit of syntactic sugar to writing a generic function. And this is a generic with a constraint. So the print area function accepts any struct as a function parameter which implements a shape trait. And this is similar to concepts in C++20. Yeah. And now a little bit of advertisement. Come to my template talk about C++20 on Friday if you want to, as well. And the really cool thing here is this generics work really similar to what we know from C++. We have different syntax for that. We have this %impl we've seen before. We can write something which more looks like C++ with the angle braces, a T, and after the colon, we write the trait it should implement. And then we can use T here as a type, and it needs to implement shape. We can force it to implement several of these traits. So maybe T needs to implement a shape trait and the density trait. And we can write it more verbosely with the where syntax, where we have in the angle brackets only the type name and the constraints here after the where we say T needs to implement display and clone, and U needs to implement a clone and a debug trait, whatever they are. And this works exactly like you would expect it in C++. Yeah? These traits work here like concepts and constraints, and the generics work like templates. So generics are also handled at compile time, so the compiler will use this generic function to stamp out real functions. So during compilation, it will see, okay, I call the shape print area function here, which needs a shape. I call it with the square struct. So I will generate just a function print area which accept a square struct. So only this is stamped out. And this is something you know from C++, and this has almost or no performance implication because this is all handled at compile time. Only difference is that you almost always need these constraints if you want to have your generic function work, because everything you do in your function block is checked against the constraints. So here, shape.area says I need an area function, and this is handled by the shape trait. If I would get rid here of this shape trait and just have T here, or another constraint which doesn't have an area function, the compiler will tell us, hey, you have a generic function here. The function parameter is of type T. You are calling shape.area here, but the traits you defined as constraints don't implement this area function. I will not compile this for you. Give me more traits or other traits. So Rust is here really restrictive in what it allows for generic functions. We are not restricted to generic functions. We can also do generic structs, but for timing reasons, I will not show this here. So next slide. Some traits can be auto-implemented. This is also really cool. So here, for example, I have the syntax which says I have a struct rectangle, and I want to have the traits clone and copy auto-derived for the struct. I don't want to implement the functions I need for these traits myself. I want the compiler to do that for me. And this can be done with this derive syntax using some macro magic. And the clone trait allows you to explicitly create a deep copy of a value, and deriving clone implements the clone message, which when implemented for the whole type calls clone on each part of the type. And this is really cool because if you derive clone and copy, you get a struct which now has copy semantics. Now, what I promised you a lot of slides ago, now we have a struct which has copy semantics as we know them from C++. And this is explicit because we need to derive clone and copy for that to work. And if one of these underlying types here doesn't support clone or copy, this will not work. It will tell us, hey, you want to derive clone or copy for something which doesn't support that. Please don't. I will stop compiling now. So basically all member variables of a struct need to be implementable using clone, or need to implement the clone trait for themselves for this to work. And this is really cool. There are other traits which can be auto-implemented, and using macros, you can write your own. If you have a look, more looks at Rust in the future, for example, if you look at serialization, there's a trait called Zerde for doing serialization to CSV or JSON. This implements, for example, serialization traits and tricks using this exact same syntax. So we can also do dynamic dispatch with traits. So a trait object can represent any struct which implements the mentioned trait. And we can use that, for example, to create vectors of different types which share a trait. And these trait objects then perform dynamic dispatch, like similar to virtual function calls at C++. And we need a smart pointer for that, like unique pointer in C++ is box in Rust, and we can have a look at that, how this would look like. So for example, if a trait animal, which forces us to implement a make noise function, we have a dog, which implements animal, we have a cat struct, which also implements animal, and then we have here interesting syntax. We have a vector, and the vector here is an explicit type given with the angle brackets for defining the generic type here. And the type is a box, so a smart pointer, a unique pointer if you want, of dun animal. Animal is a trait, and dun means that we're using this trait dynamically so that we are creating a trait object. And this allows us to create a vector which contains a smart pointer to a dog struct and a smart pointer to a cat struct. And we can now iterate over it and call the make noise function. And this is basic dynamic dispatch in Rust. The compiler checks at compile time if this makes sense. Yeah? If dog and cat implement animal is checked. If animal can be used as a dynamic trait object, there are several constraints, some types which cannot be used as trait objects. And this is all checked by the compiler, and the compiler will tell you if you've done something wrong here. So you cannot shoot yourself in the foot really with dynamic dispatch. So traits also work with functions, which is really cool. They are function traits. And I will start here with this code. So maybe you want to write a function which calls another function twice with the output as the input of the second function call. Can be something we need to do. How would we do that? So we have a generic functions with two generic parameters. And we have a constraint here which says f is of type fn t arrow t. And this means f is a function which accepts a parameter of type t and returns a t. This is a constraint for the type f, and the type t is unconstrained, and we return a t. And with that, we can write a function which accepts a function and an input value, and we can call it twice here and return the value. This is really cool. So we can use that to create like a factory for callables or whatever we want. And this is using the constraint here checked at compile time if this makes sense. And, to run this function twice. If we want to create a callable factory, this is here. So we want to create a function which returns a new function. Then we need a trait object again, because the compiler doesn't know the size of the function we are returning here. We need a smart pointer, a trait object to a function trait, and then we can create using the smart pointer here a new function. So this is a syntax for a closure or a lambda in Rust. So it's a function which takes as a parameter x and returns num times x, and move before the definition of a closure or lambda means that we move values from the surrounding scope into the closure. But since num supports copy semantics, this is just copied. And with that, we have a callable factory. So we can call callable factory here to create our function res. We can run it here. It will return 50. And we can run it twice with our run twice function, and it will return 125. And this is also really cool syntax. So Rust has built-in constraints for function types, which I really, really like. So last point in this chapter about structs. So we now had structs with like defined fields, but there are also tuples and tuple-like structs in Rust. So we can create a struct color, which just has 3 values in it, but we don't give them any name. The same holds true here for point. It just has 3 integers in it, and we don't give them names. And instead of creating them with the curly brace syntax, they are created with a normal syntax. here without curly braces, just with normal braces. We can also create tuples which don't have an own type, but just are tuples, also using the normal braces. There's a possibility to do destructuring on tuples. So if I just want the first value of my tuple, I can write this line here. Or I can do more complicated destructuring where I just want to have values RGB, which are the contents here of my tuple like struct black. And this will destructure in this way that in the variables R, G, and B, these values will then be stored. And I can use them. I can also use a point syntax and then enumerate my values. And this is really cool. And although they have the same contents here, color and point and this unnamed struct are completely different types here and can be used as different types and cannot be easily converted into each other. And now it's time for questions again. That's a question which I find really interesting. So concerning structs and member functions, is there something like a declaration or header file in Rust? So Rust has a module system. So I haven't shown you that here, but you can create several Rust files and you can define modules. And then within modules, everything is publicly visible. And outside of a module, for that visibility, you have to define what structs, functions, and members will be visible to the outside world using the pub statement. And the Rust compiler will figure out the module system itself. It works very similar to what you know from the module system, which comes with C++20. And I think since we have 8 minutes left, I have no time to showing you that in a real way. But if you go, for example, to the official Rust book at the beginning of the slides, it has a section on the module system. And basically every Rust book or Rust tutorial has a section on the module system. So, and it's a pretty well-designed module system as well. I think it's even better than that what we have now in C++20. And yeah. Last but not least, I want to talk a little bit about enums and Rust because they are different than in C++. So enums are some types in Rust, and they work a little bit like std variant in C++. And you can define different things in enums. You can just define a value here like stay, and this is then treated like just a struct without no members. You can define structs in enums with named values or tuple-like structs. And all these things inside of the enum can only be accessed via the enum. It doesn't exist without the enum. Enums can have methods with an impl block, and enums can also be generic, just like structs and functions. And for example, here I define an enum and I use the move value here, and the move I assign 12 and 15. So it's, if you're familiar with some types in Haskell, maybe this looks familiar to you, and it's more std variant on steroids in C++, I would say. We can do pattern matching in Rust. So there's a match statement for control for checking, for example, what happens with an enum we have. And this is a very powerful control flow statement, which allows us to compare a value, not only in enum, but it's often used for enums, against a series of patterns, and then execute code based on which pattern matches and also return values from that. So here my action is an enum action, and the move part of it is a struct, and we use a match keyword on it. And if it would be action stay in it, then we just return 5. If it's action move, and then we destructure the contents of move x and y, we would print moving and would return x plus y. And if it's something different, indicated by the underscore, we would just return 20. And here the code would return 27 because it's a move. We destructure x and y and add it. And this is really cool. And the compiler checks for us that we use every part of the enum. So if I would leave out this underscore here, this part, then the code would not compile because we haven't checked against all the parts which are in an enum. There's a shorthand notation for that with the if-let statement, which I will skip here now for time constraint reasons. There are some enums which come with a standard library. There's an option enum, like std optional. Either it contains something or it contains none. This is defined by the standard library, and it's cool if you have optional values. And you have to convert this option of t to the t you want before you perform operations with that. And there are checks for that you're not doing illegal operations with the none type. And this is really cool. And also, these enums are used in error handling. So there's a result enum, which contains either OK of an value or error of an error value. And you can use that in Rust to do error handling. So you can do something which possibly returns an error value, which can throw an error. So like opening a file, this returns a result. And then you can check with the message statement whether it's OK. And if it's OK, we destructure the file here and return the file handle. Or if it's an error type, then we call the panic macro, use that to print out the error message and terminate the program. And this is similar to what you will get in C++ 23 with std expected. I think std expected is inspired by Rust, but again, prove me wrong if you know better than me. There are for this result enum, there are helper methods like unwrap and accept to do this same thing I did before with the match statement automatically for you. You can write functions yourself, which return these results if you want. And there's also a question mark operator, which helps us if we want to write error handling in Rust, because it will help us to return the error value here when an error occurs, instead of having to write match over and over again and return an error to the outer scope. And this question mark operator eliminates a lot of boilerplate, because it handles returning an error here to the main function automatically when there's an error, instead of having to check that ourselves. I will skip the question here. And since we have 2 minutes left, I will also not talk about iterators, and I will just skip to the end. So Rust is cool, but if you're working on a large C++ project with like a million lines of code, you should not rewrite that in Rust, of course. It makes no sense. Maybe you can start new projects in Rust if you're interested. And interesting questions for C++ developers might be, what are options for interop here? We have Rust bindgen, which creates a foreign function interface unsafe bindings. We have the CXX creates for safe bindings with the foreign function interface. Or if you are a large project which uses services or microservices and you communicate a lot over the network or named pipes, you already know projects like gRPC and Swift, and they are also supported by Rust, and you can write a service or an interface with that. So interesting topics for further exploration with Rust. I didn't talk about multi-threading or async. Maybe the other talk I mentioned will talk about that. If you're interested in web development, Rust can be converted to WebAssembly, also interesting. And yeah,